Hey everyone, my name is Sophia Pedigo, and today we're going to be looking at a problem in which we have these two spherical tanks. Now, for each of these tanks, we have a flow rate going in. So this one I'm just going to call tank 1. And we have a flow rate going into that tank called Q1N. Now, for tank 2, we have a similar setup in which there is a different flow rate called Q2N, which is flowing into the tank. Now, each of these tanks is at an initial steady state. So the liquid in tank 1 is at some initial steady state height, which we'll call H1. And tank 2 is also at an initial steady state. So the liquid inside this tank is at a steady state height too. Now, another thing to note about these tanks is that there's a pipe connecting both of these tanks, and there's a flow rate going out of the tanks. So for tank 1, we're going to call this flow rate Q12 because it's flowing from the first tank Q1 to Q2, tank 1 to tank 2. And for tank 2, we're going to call this flow rate that's leaving at Q2. And what we want to do today is we want to see if we can derive steady state equations for the flow rate out of the tanks and use that information to find differential equations for the time variation of these tanks and the height. So let's go ahead and look at these flow rates that I just wrote down, Q12 and Q2. These are the flow rates leaving the tank. Now, what we know about the flow rate is the flow rate is going to be equal to the area of the pipe here, which we're given A12, the area, and A2. So this A12 is just the area of this pipe here that's going from tank 1 to tank 2. And area 2 is the area of the pipe that is leaving tank 2. So we're given that. I'll go ahead and write that down. So we know that Q12 is going to be equal to the area 12 multiplied by the velocity of the fluid that's leaving that tank. And likewise, the flow rate leaving tank 2 is going to be equal to the area of that pipe leaving tank 2 multiplied by the velocity leaving tank 2. So we've got a good start here. We know what the area is, we're given that. But the problem here is that we don't know what the velocity is. So what we're going to do is look at a similar problem that's going to give us an equation for the velocity. So let's go ahead and do that. I'm going to section this part off here so we don't get confused. And we're going to look at a similar tank problem, but this time it's a cylinder. So the cylinder's got some fluid in it, and we're going to be looking at position 1. And down here, there's going to be a second position, and there's going to be fluid that's flowing out of this cylindrical tank. And we can model this using Bernoulli's equation. So we'll go ahead and do that. That's going to give us, it's going to be the change in pressure. So we've got P2 minus P1. And for the sake of simplicity, we're going to say that the fluid is the same. So it's going to have the same density, which I'm going to use rho to represent. Now, to that, we're going to add the acceleration of time multiplied by the height difference. So that's going to be H2 minus H1 plus, and to this, we're going to add the velocity V1 squared minus V2 squared. So the change in velocity divided by 2, and that's going to be equal to 0. Now, a couple of things. Velocity, hold on, I'm sorry. That is flipped. This should be V2 squared minus V1 squared. So first of all, let's go ahead and look at V1 squared. V1 is going to be this huge cross-sectional area, and that velocity is actually going to be very close to 0, so we're just going to say it's 0, and that term is going to cancel out. Now, the important thing to note about this container is that it is open to the atmosphere. So the pressure at 1 is going to be equal to the pressure at 2. So P2 equals P1, which means this term cancels out here. Now, what we're left with is the acceleration due to gravity multiplied by the change in height. I'm just going to call that delta H. And that is going to be equal to negative V2 squared over 2. Now, earlier what I said is that we didn't know what the velocity was in our flow rate equations. Well, now I'm looking at a similar problem in which we have a cylindrical tank, and I'm just about able to find the velocity for this. Let's go ahead and keep solving and see if we can make a substitution into our flow rate equations that I found earlier. So if we rearrange this and solve for V2, we end up with V2 equals the square root of 2g delta H. And as it turns out, this equation actually is the same for the spherical tanks that we have over here. So we can just go ahead and substitute that in and use it to solve for the flow rates. So let's go ahead and do that. I'm going to go ahead and write this velocity equation up here just so we don't forget what it is. So any velocity, I'm just going to write V is equal to the square root of 2gh. And I'm going to go ahead and erase this. Now that we know that, we can make the substitution into our flow rate equations. So we're going to go ahead and do that. And we're going to say that Q12 equals the area 12. We're given the area, so we don't need to solve for that. We can make our substitution in for the velocity. So we have the square root of 2g multiplied by h1 minus h2. Now you might have noticed I don't have any brackets around the h2, the height difference term, and I want to go over that really quick. So for our initial steady state, we can see that height 1 is taller or higher than height 2. When we subtract that number, we're going to end up with a positive number in this case. However, later on, we're going to be looking at differential equations in which there's a time variation with the fluid height. And we don't know if H1 is going to be higher than H2 or if it's going to be lower. And if it's lower, that's going to give us a negative number, and we can't take the square root of a negative number. So I'm going to put the absolute value of the height change in. And also, we don't know, I have it drawn as H1 is higher than H2, but we don't know that that's always going to be the case for our steady state. So regardless, we're just going to go ahead and put that absolute value sign in so we don't end up with a negative number that messes things up. Now that we've got that, let's go ahead and do the same for Q2. So Q2 is going to be equal to the area at 2 multiplied by 2g h2. Now, I'm going to go ahead and erase all of this and rewrite the equations up here so we can set those aside for later. Because if you'll notice, we were actually able to solve the first part of this problem, which was find steady state equations for the flow rate out of these spherical tanks, which we've done. So our first equation is going to be Q12 equals A12 multiplied by 2g absolute value of h1 minus h2. And our second equation is going to be Q2 equals A2 square root of 2g h2. I'm going to erase all this here. Now, what we're going to look at next is differential equations for the time variation and fluid height. This is a little bit trickier, but we can do it. We know that we're going to have, we want the height ultimately. We want the time variation and fluid height in a differential equation. But the easiest way to go about this is going to be to first look at the variation of volume with time. So let's go ahead and write that out just for the first tank here, okay? So we're going to have the differential change in volume for tank 1, so dV1, over the change in time, dt. And we know that there's a couple of flow rates going in and a couple of flow rates going out for the tank. Specifically, we have Q1 in, so let's go ahead and write that down. It's going to be a positive number. It's going into the tank. We have Q1 Q1N. And then we have a flow rate leaving the tank, specifically Q12. So we're going to subtract that. We're going to say Q minus Q12, right? So that's good. We've got an equation, but you'll notice that we found that, did it right up here. So let's go ahead and make that substitution. We'll say dV1 over dt equal to Q1N. We're given that number, so we don't need to make a substitution there. Minus, let's see, A12 square root of 2G H1 minus H2. However, we're working with a slightly different situation here. Before we had a steady state in which we knew that the heights weren't changing, it was steady. We had H1, we had H2, and we said that we for sure knew that Q12 was leaving the first tank. But in this situation, it's a little bit different because this equation is varying with time. So we don't know for sure if this flow rate, Q12, is always going to be leaving the tank. We might have a situation in which the height here is higher and it's going to flow the other way, and Q12 is going to be going into tank 2. So in order to adjust for that, we're going to take this sign. And when I say sign, I don't mean like a sine function. I mean the actual sign, negative, positive, of this difference in height. So let me write this one more time. We're going to end up with the differential change in volume of tank 1 over the change in time is equal to Q1N minus, we're going to go ahead and put the minus sign. But in order to correct for whether or not the flow is going into the tank or leaving the tank, we're going to say sine of H1 minus H2 multiplied by A12 multiplied by the square root of 2G absolute value of H1 minus H2. And that's going to be our change in volume with the change in height for the first tank. Let's see, you can't really see that, so let me adjust that. There you go. So we've got, just to go over this again since you couldn't quite see, the change in volume with the change in time is equal to the flow 1 into tank 1 and minus the sign of H1 minus H2 to adjust for whether that's flowing in or out of the tank, multiplied by the area of the pipe, multiplied by the square root of 2G, absolute value of H1 minus H2, which is just our velocity. So let me go ahead and erase this top part. I'm going to write this down as equation 3. Oh, I'm not working with flow rates anymore. This time we've got dV for volume 1 equals Q1N minus sine H1 minus H2, running out of room here, A12 square root of 2G absolute value H1 minus H2. Okay, now I want to keep in mind that we are asked to solve for time variation and fluid height. Right now I've got it in volume and time variation. We're going to come back to that, but for right now, we're just going to be looking at volume, and then I will look at height difference once we get some equations for this. So before I get the height difference, I want to look at the volume change for the second spherical tank. This is going to be pretty similar to what we just did for the first spherical tank, but there's going to be some differences. So let's just go ahead and write this down like we did last time. We're going to have dV2, the differential change in volume for tank 2 with respect to time, is going to be equal to, this time it's a little bit different. We've got Q2N, the flow rate going into the second tank. So that's going to be positive. We're assuming that's always going to be flowing into the tank. Q2N. Now, we're going to go ahead and say that we're going to add Q12. So we're going to just say we're adding Q12 because at least in the situation that I have drawn here, Q12 would be flowing into tank 2. However, we are going to make an adjustment with the sign. So that would be Q12, which is right here. So we'll have plus sign of H1 minus H2, A1, 1, 2, square root of 2G, H1 minus H2. So that's going to be the flow rate of Q12 going into the second tank. And then we're going to add on another term because for the second tank and the situation that I have drawn here, we have Q2 flowing out. So this time we're going to subtract, and I'm just going to write this on kind of the next line down here. So we're going to say minus, and we're going to adjust for the sign change because potentially this could be flowing the opposite direction and going into Q, the second tank. But we'll say that it is going to be, we've got Q2 here, so we'll say, oh, you know what? No, we don't need to adjust for we don't need to adjust the sign because we just have the height of 2. Sorry about that, ignore that. We're just going to have the area of 2 multiplied by the square root of 2G H2. And that is our equation for the change in volume with respect to time for the second tank. So I'm going to write this down again. I'm going to kind of shift things because I'm running out of room here. But we're almost done. So this is the differential change in volume with respect to time for the second tank. That's going to be equal to Q2N plus, we still need to adjust the sign for the flow rate from 1 to 2, sine of H1 minus H2 multiplied by the area of 1, 2 multiplied by the square root of 2G H1 minus H2. And then minus the area to square root of 2G H2. Okay, that's kind of a lot, but we're getting close to finishing. So like I just said, or I said a little bit earlier actually, we're really solving for the differential equations for the time variation and fluid height. Right now we have the volume and time variation, which is a little bit different. So in order to account for that, we really need to divide both of these equations that I just solved for in order to get dH dt. We need to divide both of them by the cross-sectional area of the pipe. So we're going to go ahead and look at a circle here that's going to represent the cross-sectional area that we're looking at. And we know a couple of things. We know that we're given the radius, right? So let's go ahead and draw that in. And I'll just represent this with lowercase r, right? And we know that as the height changes here, so we've got some height here, we've got some height here. We can use a triangle to represent this, where this is going to be the radius. This is going to be the radius with respect to time, because it could be, could be down here, could be down here, could be, all the way up here or somewhere down here. That's going to be the radius with respect to time. And then this value here is going to be, well, I should say this value here would be the height with respect to time. So this right here is going to be the height with respect to time minus r. Now we've got a triangle here, and ultimately what we're trying to do is find a cross-sectional area of the tank, which we can use to find the differential, incorporate that into these equations to find the differential equation that shows the variation of time and fluid height. So we're looking at the tank height right now and trying to find an equation that represents that. So we can use the Pythagorean theorem to kind of rearrange this, and we would end up with r squared is equal to the radius with respect to time squared, plus the height. Well, I'll just go ahead and write the height because that's a little bit easier. The height minus r, that quantity squared. Now, we want to get this term by itself, so we have an equation of radius with respect to time. So let's go ahead and rearrange this, and we're going to end up with, let's see, RT squared equals r squared minus h minus r squared. And we know that the area of a cylinder, or not a cylinder, is going to be equal to pi r squared. And so we have r squared with respect to time, so we can make that substitution in for pi and divide our equations or differential equations by this term and end up with the differential change in height with respect to time, which is what we were looking for. So let's go ahead and do that. I'm going to erase this. And down here, I'm going to write this all together. So bear with me here. We're going to have our fifth equation, which I'll write right here if you can see that. Equation number 5 here. And that is going to be equal, the cross-sectional area, which I'll say is AC, is going to equal pi multiplied by this quantity here, because you can see that we're looking for r squared, and we have r as a function of time squared, which is what we're trying to find. So this is going to be pi multiplied by r squared minus h minus r squared. And then, like I said, now that we have the cross-sectional area as a function of time, we can go ahead and put that into our differential equations and get the change in height with respect to time instead of the change of volume. So let's go ahead and do that. I'm going to start with this equation here, which was the change in volume for tank 1. And this is going to become dH1 over dt is equal to the flow rate right here, Q1N, minus the sine of H1 minus H2, multiplied by this area A12, multiplied by the velocity of the fluid leaving tank 1, which we found out to be 2g, absolute value of H1 minus H2, divided by this cross-sectional area that we just found, which is pi multiplied by radius 1, which we've got right there, minus height 1, which we have right there, minus radius 1 again, that quantity squared. And now we've got a differential equation for the differential change in height with respect for time for the tank, the spherical tank 1, which is great. And now we can do the exact same thing for the second tank. I'm going to go ahead and erase this equation here for the cross-sectional area. And so we're going to look at equation 4 now, and we'll end up with dH2 for tank 2, dt is equal to, I'm going to kind of write small so I don't run out of space here. It's going to be equal to that flow rate that's going in, Q2N, plus this quantity, which is the flow rate 1 to 2 going into that tank, but we're adjusting for the sign in case it happens to be going the opposite direction. Sine of H1 minus H2 multiplied by the area 1, 2 square root of 2G H1 minus H2. And then we've got this flow rate Q2 leaving, which is just minus A2 square root of 2G H2. And we're going to divide this by the cross-sectional area of the tank. So we're going to have pi. Now it's important not to get confused. I have radius 1 here because we were looking at radius 1 in the first tank, but now we're looking at radius 2 in the second tank. So R2 minus H2, because we're working with the second tank, minus R2 squared. And that is going to be our second equation. Let me make sure you can see this all right. That's going to be our second equation for tank 2, which shows the time variation in fluid height. So ultimately what we were able to do is we were able to find an equation for the flow rate leaving this first tank, Q12, an equation for the flow rate leaving the second tank, Q2. We were able to put those together to find differential equations which showed the variation in time variation in fluid height. And then we were able to find the cross-sectional area of these tanks here. And we were able to use that to find the differential change in height for the tanks with respect to time. In my next video, what we're going to be looking at is we're going to look at coding this problem out in Python using actual values for the heights. And we're going to find the initial steady state flow rates out of these tanks. And then we're going to be able to look at the variation in height with time using Google Colaboratory. So that's all for right now. I'll see you in my next video.